Welcome to our final presentation for CICI 401. Our project is Elasticsearch for Sparkler. Our team consists of 5 members. We have Felix, Miles, Nikhil, Caesar, and Kevin. And we are working for a stakeholder, Dr. Louis McGibney, who is a data scientist working at NASA JPL. His fields of expertise include information retrieval, web search, databases, natural language processing, and much more. Dr. McGibney is a maintainer of Sparkler, an open source web crawler of the Apache Spark Foundation. Our task was to contribute to this project. So first off, what is Sparkler? Sparkler is a web crawler built off of the Apache Spark framework. At a high level, the crawler visits an initial website, scrapes text, information, and links off of the page, and stores this information into a database. It then repeats this process on the found links. The current storage engine for Sparkler is Apache Solr.
So Sparkler has been built from the ground up with Solr in mind as its storage engine. However, as the popularity of the project grows, there has been growing community desire for additional storage engines. The most immediate of these is the widely popular Elasticsearch. Given this, the goals and desired impact of our project was to enable an Elasticsearch integration with Sparkler, and broadly speaking, refactor Sparkler code so that it makes it easier to add integrations with additional storage engines in the future. Our stakeholder provided us with a broad set of outcomes to help us reach this goal, and we analyzed these objectives and sequenced our project as follows. Our first objective was to create containers for Elasticsearch and Sparkler. The goal here was to get contributors and users of Sparkler wishing to use Elasticsearch up and running quickly if they did not have an existing Elasticsearch deployment. Our next objective was to modify Sparkler internals to add generic support for storage engines and specifically for Elasticsearch. Additionally, we had the broad objectives of adding tests and documentation for any new systems that we added.
Now, in terms of the overall project architecture and the design patterns that we used, let me start with the monolithic architecture. So Sparkler used the monolithic approach, meaning that the UI, the database, and the backend code were all together in one code base. And because of this, we decided to approach the project using the factory pattern in order to make Sparkler more flexible for new storage engine support. To do this, we decided to create interfaces for the storage APIs and then write connectors for Solr and then Elasticsearch. We also decided to use the singleton design pattern in order to efficiently store Sparkler properties for storage and querying the database.
For our development, we created GitHub issues on the main open source repository for tasks we were working on, and wrote code in the forked repository in branches whose names match those of the issues. We created pull requests from our forked repository to the main repository when the new features are finished. Then we reiterated with our stakeholder and updated our code further until the pull requests were approved and merged into the main repository. Some challenges we faced during development were that we used the GitHub project board to keep track of assignments and the status of individual tasks at the beginning of the project, but we couldn't form the habit of updating them on time toward the end. Instead, we mainly used our Slack channel to communicate our progress. As for teamwork, some challenges we faced was that the times when all the team members were available was limited. So at the beginning of the semester, we had some trouble arranging meetings. We were able to mitigate this issue by dividing the whole team into subgroups of 2 or 3 people as we worked on separate tasks at different stages of the project. Splitting the team into smaller subgroups not only helped us arrange meetings more easily, it also made our development more efficient, as the subgroups then held pair programming sessions to efficiently produce high-quality code.
So expanding on the non-technical issues, let me discuss the legal, professional, and security-related issues. So first, the legal ones. So because we are integrating new external software, we had to adhere to that software's license. But because Elasticsearch had a public version, we didn't run into any major hiccups. Now, in terms of the professional issues, Sparkler was an existing project handled by a lot of different contributors around the world. And they had set up a very efficient pipeline for creating issues and new pull requests. And so to make sure that the workflow proceeded as expected, we had to follow those guidelines. Additionally, every time we pushed code, we had to make sure that we didn't introduce anything like regressions and keep the quality of the code to a high standard. And lastly, for the security related issues, because we were adding so much new code to Sparkler, we had to ensure that we didn't introduce any new vulnerabilities.
We used a variety of skills and tools during this project. The main tool we used was a Scala programming language, as the existing code was already written in it, and all of the code we added to the project was also written in Scala by us. We also used Python scripts to automate the deployment and to start and stop our Docker containers. During the refactoring, we interacted with the Apache Solr connector for Java, and we also added the Elasticsearch Elasticsearch storage connector to our project to interact with the local instance of Elasticsearch. We used Apache Maven to manage those dependencies and the build system. The project makes big use of the Apache Spark framework, and while working on it, we used some of the API functions provided by the framework. We used GitHub issues and pull requests to manage our code and got it approved by our stakeholder. We used a variety of USC classes in this project, which I will list here. I will touch on the most important ones. CSCI 201 and 310 were really important for us because it taught us Java and advanced Java development. As I mentioned before, the project was written in Scala, and those two languages are very similar. Also, CSCI 350 was very important because it taught us about containerization. And during a directed research project for CS 490, we learned about Docker and Docker Compose. Even not strictly a CS class, EE 451 Parallel and Distributed Computing had labs about Apache Spark, which helped us during the development. And last but not least, we used 2 ATP classes to learn about Python and design patterns.
So in terms of continuing professional development, a lot of it is related to the skills and tools mentioned before. For example, the Docker containerization, the distributed systems and computing, Solr and Elasticsearch storage engines, web crawlers, and much more. But there are also other more conceptual ideas like design patterns and configuration management and unit tests that were very important as well. So I just want to say that we would like to thank all of the people who are involved and helpful in this project. We really appreciate all your help, and thank you for watching.